The exponential and the log derivatives are going to be defined derivatives as well. We are going to just define the derivative of e to the x as itself e to the x. And this is actually very unique because this is the only derivative whose derivative function is itself. So the slope function is the y values of itself. Okay, so if I take the y value at any point of e to the x, that actually gives me the slope at that point. The a is a derivative, a to the x is an exponential. Now, just like e to the x, it generates itself a to the x. However, since we're not using a base e, we have to count for it with a log a attached to it. So this log a is just a coefficient that we use to account for a non-base e. In calculus, base e works very nicely. Any other base kind of is awkward. So we want to use base e whenever possible. But we can account for non-base e with that log a. The log x we're going to define as the derivative of log x gives us 1 over x. And you may have seen some examples of this where the graph of log x, the derivative seems to match the positive side of the 1 over x function. But again, this is a defined derivative. We're going to define it as this, and this goes on our formula sheet. We need to get to know these defined derivatives. And the log becomes 1 over x. If we don't use base a, we still get the 1 over x function. Okay, so we're still generating the 1 over x here, but we have to count for the non-base a by dividing by log a. And that's just because we're not using a base e. When we use the base a, we just account for it by dividing by log a. When we use base a for exponents, we multiply by log a to adjust for the non-base e.